Our entire cosmic rulebook rests on a handful of unchanging numbers. These are the constants of nature, the fixed settings of reality that let us predict everything from a falling apple to the fate of a star. But what if those settings are not locked in place? This is not a wild fantasy. It is a serious scientific investigation that could dismantle our most fundamental theories. By the end of this journey, you will understand how the very fabric of reality could be rewriting its own laws. We will explore whispers from ancient light suggesting the rules of physics differ across the cosmos, and confront the chaos that would unfold if the speed of light itself began to drift. How much of what we know about the universe is built on a foundation of sand? Think of the universe as an intricate machine, a cosmic clockwork of unimaginable complexity. For it to run at all, for it to produce galaxies, planets, and life, its gears must be set to very specific, precise values. These are the constants of nature. They are not things you can see or touch. They are pure numbers, the fundamental settings woven into the fabric of space and time itself. They are the numerical dials that were set, presumably at the moment of creation, and left untouched ever since. The most famous of these is the speed of light in a vacuum, represented by the letter c. Its value is about 299,792,458 meters per second, and according to Einstein's theory of relativity, nothing in the universe can travel faster. This number is the ultimate speed limit, the cosmic constant that links space and time into the single entity we call spacetime. Then there is big G, the gravitational constant. This is the number that tells us the strength of the gravitational pull between any two objects in the universe. It is the key value in Newton's law of universal gravitation and in Einstein's equations for general relativity. Without a fixed value for G, we could never calculate the orbit of the moon, the pull of a black hole, or the expansion of the cosmos itself. Perhaps the most intriguing, however, is a less famous constant called the fine structure constant, denoted by the Greek letter alpha. This one is a pure dimensionless number, roughly 1 over 137. It is a magical combination of other fundamental constants, governing the strength of the electromagnetic force that holds atoms together. It determines how tightly electrons bind to an atomic nucleus, which in turn dictates the entire language of chemistry, the color of light atoms emit, and the very stability of matter. These numbers and a few others like them are the bedrock. They are the immutable values we plug into our most profound equations, from the quantum realm to the cosmic scale. Their presumed constancy is the foundation of all predictive science, because we trust that the speed of light today is the same as it was 5 billion years ago. We can look at the light from a distant quasar and understand the universe's history. Because we assume the fine structure constant has never wavered, we can be confident that the atoms in our bodies behave exactly like the atoms in a star 10,000 light-years away. This trust in eternal numbers is what allows us to map the cosmos, to rewind the clock to the first moments after the Big Bang, and to believe that the laws of physics are truly universal. Our entire understanding of reality is built on this one quiet assumption that the rules of the game do not change. This profound trust in eternal numbers has not gone unquestioned. For nearly a century, a quiet unease has simmered among physicists and philosophers alike. Why are these constants set to the exact values they are? Why is the speed of light 299,792,458 meters per second, and not a little faster or slower? The great physicist Paul Dirac was deeply troubled by what he saw as the arbitrary, almost random nature of these fundamental numbers. He wondered if their apparent constancy was merely a local condition, a temporary feature of our corner of spacetime, and that over cosmic distances or timescales they might slowly drift. This philosophical puzzle taps into something even more profound known as the fine-tuning problem. It is the startling realization that our universe seems suspiciously well set up for life. If the gravitational constant, big G, were just a few percent stronger, stars would burn their fuel too quickly and violently, collapsing into black holes before life could ever arise on orbiting planets. If it were slightly weaker, stars might never ignite at all. The fine structure constant, alpha, is even more delicate. If its value differed by even 1% in either direction, the bonds that hold carbon atoms together inside stars would fail. Carbon, the essential building block of life as we know it, would never be forged in stellar furnaces. The universe would be a sterile place filled with hydrogen, helium, and little else. This cosmic precision feels less like a happy accident and more like a carefully calibrated setting. It naturally forces a monumental question upon us. Are these constants fixed and eternal, a permanent part of reality's blueprint, or could they be more like cosmic dials that were set during the Big Bang and have perhaps been slowly turning ever since? What began as a philosophical mystery, a source of wonder and debate, has now hardened into a concrete, testable scientific hypothesis. The fine structure constant, alpha, has become the prime suspect in this cosmic investigation. Among all the fundamental numbers, it stands out as the most likely to have changed. The reason lies in its unique nature. While the speed of light or the gravitational constant are tied to specific units of measurement, alpha is what physicists call a dimensionless constant. It is a pure number, a ratio that emerges from combining other constants. This makes it a true property of the universe itself, independent of any human-made measuring system. If the laws of physics are shifting, alpha is where we would expect to see the fingerprints. Its value dictates the strength of the electromagnetic force, the glue that holds our world together at the atomic level. Change alpha and you change everything. A slightly stronger electromagnetic force would make electrons cling more tightly to their atomic nuclei. This would shrink atoms, alter the energy levels within them, and completely rewrite the language of chemistry. The bonds that form molecules, the reactions that power life, even the very color of light that atoms absorb and emit, all would be different. Most critically, it would change the nuclear reactions inside stars. The delicate balance that forges carbon, the element essential for life, could be thrown off entirely. A universe with a different alpha might be a universe without carbon, and therefore without us. This profound connection to the very possibility of life is why scientists are so intent on hunting for any drift in alpha's value. They are not just testing a number, they are testing whether the universe's capacity for complexity is a fixed feature or a fleeting accident. To search for this change, astronomers turn into cosmic detectives, using the universe itself as a time machine. They point powerful telescopes at the most distant, ancient objects in the cosmos, quasars that shine from billions of years in the past. The light from these quasars has traveled across the universe for eons, and on its journey, it passes through vast clouds of interstellar gas. Atoms within those clouds absorb specific wavelengths of this ancient light, leaving dark lines in the quasar's spectrum like a unique barcode. The precise position of these absorption lines is dictated by alpha. If the value of alpha was different when that light was absorbed billions of years ago, the entire barcode would be subtly shifted. It would be as if a musical instrument, tuned to a specific note long ago, was found to have played a slightly different pitch. By comparing the barcodes from ancient gas clouds with those produced in laboratories on Earth today, scientists can look for that telltale shift. They are reading the fine print in the oldest light in the universe, searching for a single line of code that may have been rewritten. This search for a shifting cosmic signature is a monumental task of precision. Astronomers act as forensic scientists, examining the oldest evidence in the cosmos. Their primary tool is the light from quasars, the brilliant cores of galaxies so distant their light has been traveling for over 10 billion years. As this ancient beacon journeys toward Earth, it passes through immense, diffuse clouds of gas floating in the vast emptiness between galaxies. Atoms within these clouds, hydrogen, magnesium, iron, and others, act like selective filters. They absorb very specific colors or wavelengths of the quasar's light, each atom leaving a unique dark mark in the spectrum. This creates a detailed barcode of absorption lines, a chemical fingerprint imprinted on the light by the ancient gas. The exact position of each line in that barcode is set by the fine structure constant, alpha. It is the universe's own tuning fork. To see if the universe's tuning has changed, scientists compare this ancient, fossilized barcode with the one produced by the same atoms in laboratories on Earth today. If the value of alpha was different billions of years ago in that distant gas cloud, the entire pattern of lines would be minutely shifted. It would not be a uniform stretch, but a subtle, telltale rearrangement, as if the notes of a cosmic chord had drifted slightly out of sync. Detecting this shift requires extraordinary precision, like trying to measure the width of a hair from several miles away. This is the painstaking work of large international collaborations using the world's most powerful telescopes, like the Very Large Telescope in Chile and the Keck Observatory in Hawaii. For nights on end, they collect the faint, ancient light, splitting it into its constituent colors with instruments of incredible sensitivity. They are not just taking pictures of the distant universe, they are performing a direct spectral autopsy on time itself, reading the fine print written by atoms when the cosmos was young. The results of this cosmic forensics would either cement our foundations or reveal they have been slowly crumbling all along. The results of this cosmic forensics have ignited one of the most heated debates in modern physics. In the early 2000s, a team led by astronomer John Webb at the University of New South Wales made an extraordinary claim. After analyzing the light from over 300 distant quasars, their data suggested the fine structure constant, alpha, was not the same everywhere. More shockingly, the variation was not random. It seemed to follow a pattern across the sky, a kind of cosmic gradient. In one direction, roughly toward the constellation Aquarius, the data hinted that alpha was slightly smaller billions of years ago. In the opposite direction, toward the constellation Draco, it appeared slightly larger. This pattern, dubbed the Australian Dipole, suggested the universe might have a preferred axis, a fundamental lopsidedness to its laws. The implication was staggering. It meant the laws of physics might not be isotropic, a scientific term meaning the same in all directions. Our deepest assumption of a uniform, featureless cosmos, where the rules are identical whether you look left or right, would be fundamentally wrong. The universe would possess a hidden directionality, like a subtle grain in the wood of reality itself. This was not merely a change over time, it was a variation across space, implying the very constants could depend on where you are in the cosmos. The potential discovery sent ripples through the scientific community, promising to rewrite textbooks. Yet in science, extraordinary claims demand extraordinary verification. In the years since, other teams using newer, more precise instruments on telescopes like the Very Large Telescope in Chile have conducted their own meticulous surveys. Many of these subsequent studies have failed to confirm the dipole signal. They looked at different sets of quasars, applied refined analytical techniques to account for potential systematic errors, and found no statistically significant evidence that alpha varies at all. The controversy is now a central puzzle. Is the Australian dipole a glimpse of a profound new truth, a faint but real crack in the foundation of physics? Or is it a monumental statistical fluke, a ghost in the data born from the immense difficulty of the measurement? The current state is one of active, respectful debate. Both sides acknowledge the staggering precision required and the immense challenge of pulling a signal from the noisy depths of cosmic time. This unresolved tension is not a failure of science, but its very engine. It forces better tools, sharper questions, and a relentless pursuit of clarity. The fate of our cosmic constants hangs in the balance of this dispute. While the debate over alpha continues, another constant presents an even more foundational threat. The strength of gravity itself, big G, is under scrutiny. This number is the anchor of cosmic structure, governing the fall of an apple and the orbit of galaxies. If its pull has weakened over the eons, the implications would unravel our story of the cosmos from the very beginning. Einstein's theory of general relativity assumes G is absolutely fixed, an unwavering cornerstone. But almost as soon as he published his masterpiece, other physicists began to wonder. Could gravity be a force that slowly fades? In the 1960s, theorists Robert Dicke and Karl Brans proposed a modification to Einstein's equations, now called Brans-Dicke theory. In this framework, the gravitational constant is not a fundamental number handed down from creation. Instead, it is a field, a kind of invisible energy that permeates space and can gradually change its value over cosmic time. Think of it like a spring slowly losing its tension. In the hot, dense early universe, gravity in this model would have been stronger, its grip more fierce. As the universe expanded and cooled, that grip would have subtly relaxed. This is not a minor tweak. A weakening gravitational constant would have profound effects on the universe's expansion history. In our standard model, the universe's expansion rate is governed by a tug of war between the outward momentum of the Big Bang and the inward pull of gravity from all the matter and energy within it. If gravity was stronger in the past, it would have acted as a more powerful brake, slowing the early expansion more dramatically than we currently calculate. To match the vast, relatively sparse universe we see today, this would force a radical rewrite of the cosmic timeline. The universe might need to be much older than our current estimate of about 13.8 billion years to have reached its present size against that stronger early drag. Alternatively, the initial explosive force of the Big Bang would have had to be far more violent to overcome it. This single variable change throws the entire cosmic biography into question. The formation of the first galaxies would also be deeply affected. Structures grow from tiny ripples in the early universe, clumping together under their own gravitational attraction. A stronger gravity in that ancient era would have supercharged this process, causing galaxies to form earlier, faster, and potentially in a different pattern than our telescopes observe. Astronomers meticulously map the large-scale structure of the universe, the great cosmic web of galaxies, and compare it to supercomputer simulations. A varying G would make our most sophisticated simulations, which assume a constant pull, fundamentally inaccurate. The very distribution of galaxies across the sky could be a silent record of gravity's fading strength. Testing this idea is incredibly difficult, as measuring G with high precision across cosmic time is a monumental challenge. Yet, if evidence were found, it would mean that the force which literally holds the cosmos together is not a steadfast rule, but a story slowly changing its own plot. Yet the most radical challenge to our cosmic rulebook would come from a single, sacred number changing. The speed of light, c, is not merely a measurement. In Einstein's relativity, it is the cosmic glue that binds space and time into a single, flexible fabric called spacetime. It is the ultimate speed limit, the constant that defines causality itself, the rule that no information, no influence can travel faster. This is why the idea of a variable speed of light is so profoundly unsettling. We are not talking about light slowing down as it passes through water or glass, a common physical effect. This is about the fundamental upper speed limit of the universe, the very geometry of reality. being different in the past or in different corners of the cosmos. This radical idea was once seriously proposed as a solution to one of cosmology's greatest puzzles, the horizon problem. When we look at the cosmic microwave background, the ancient afterglow of the Big Bang, we see a universe of remarkably uniform temperature. Yet, according to standard cosmology, distant regions of the early universe were too far apart for light or any influence to have traveled between them and evened out their temperature. They were outside each other's horizon, forever separate. How did they coordinate? The leading solution is cosmic inflation, a brief, hyper-fast expansion of space itself that smoothed everything out. But some physicists like Joe Megiddo offered a daring alternative. What if, in the universe's first frantic moments, the speed of light was not a fixed limit but was vastly higher? If light could travel infinitely fast at the beginning, then every corner of the newborn cosmos could have communicated instantly, achieving that smooth temperature we observe today. As the universe cooled, the speed of light would have then dropped to the value we measure now. This variable speed of light cosmology was a direct rival to inflation, proposing a different kind of dramatic event to solve the same cosmic riddle. The consequences of a shifting sea, however, extend far beyond solving one puzzle. They unravel the very framework of modern physics. In relativity, c is not just a speed, it is the conversion factor between space and time. It is the reason we talk about spacetime as a single entity. If c were different, the relationship between distance and duration would be fundamentally altered. The famous equation E equals mc squared tells us that mass and energy are equivalent, with c squared acting as the conversion factor. If c were larger in the past, the energy locked within matter would have been unimaginably greater, turning the early universe into a furnace of even more ferocious intensity. The delicate nuclear reactions that forged the first light elements would have proceeded at completely different rates, potentially leaving us with a cosmic abundance of elements that bears no resemblance to what we actually observe. Furthermore, our entire understanding of cosmic distances would become untrustworthy. Astronomers measure the vast gulfs between galaxies using the fact that light's speed is constant. We look at the redshift of light from a distant galaxy, interpret it as the stretching of space over time, and calculate how far away the galaxy is and how long its light has traveled. If the speed of light was different when that journey began, every single one of those calculations would be wrong. The cosmic distance ladder, the carefully constructed scale we use to map the universe, would be built on a foundation of shifting sand. The universe's estimated age, its expansion history, even the inferred existence of dark energy, all of it would be thrown into question. To consider a variable c is to watch the cornerstone of 20th century physics begin to tremble, forcing us to wonder if the geometry of reality itself is a story still being written. These whispers of shifting constants demand a new kind of physics, a framework flexible enough to accommodate a universe that rewrites its own rules. The good news is that such frameworks already exist, not as wild speculations, but as elegant, mathematically rigorous extensions of our most successful theories. They offer a home for the idea of change. Among the most prominent are scalar tensor theories. To understand them, we must first meet the scalar field. Imagine an invisible, intangible presence that fills every cubic centimeter of the universe, like a cosmic weather system. At every point in space, this field has a value, a number, and that number can change slowly over time or vary from one region of the cosmos to another. In these theories, what we perceive as a fundamental constant, like the strength of gravity big G, is not a fixed number at all. It is actually the present-day manifestation of this underlying scalar field. The field's value here and now determines the pull we feel, but in the distant past or in a galaxy far, far away, where the field might have had a different value, the strength of gravity would have been different too. The constant becomes a snapshot of a deeper dynamic process. This is not a clumsy patch job on Einstein's equations. It is a profound shift in perspective, where the laws themselves are woven into the evolving fabric of the cosmos. Another compelling framework comes from Kaluza-Klein models, which propose that our universe has more than the three spatial dimensions we experience. In these theories, the extra dimensions are curled up on themselves, fantastically tiny and hidden from our view. The size and geometry of these hidden dimensions are not fixed. They could vibrate or evolve, and here is the breathtaking connection. The constants we measure in our four-dimensional world, like the fine structure constant, are directly linked to the size of these curled-up dimensions. If the hidden dimensions were smaller or larger in the ancient universe, our constants would have had different values. In this view, the dials of reality are not turning arbitrarily. They are the cosmic echo of a higher dimensional geometry slowly settling into place. These theories are powerful because they do more than just allow for variation. They often arise from attempts to solve physics' greatest challenge, unifying gravity with quantum mechanics. The variation of constants is not the goal, but a natural, testable consequence of a deeper, more unified theory of everything. They transform a disturbing anomaly into a potential clue, a guiding light toward a more complete understanding of reality. The search for changing constants becomes a hunt for the hidden architecture of the cosmos itself. But if these constants are tied to evolving fields or shifting dimensions, when did they change? The most dramatic rewrites of the cosmic rulebook likely happened not over billions of years, but in the first unimaginably fleeting moments after the Big Bang. In those extreme conditions of almost infinite density and temperature, the universe was a seething, unified broth of forces and dimensions. According to many of these advanced theories, the constants were not constants at all, but wildly dynamic variables, fluctuating and settling like a stormy sea calming into a gentle lake. This process of cosmic settling is understood through the idea of symmetry breaking. Imagine a perfectly round, hot ball balanced on the tip of a needle. This state has a high degree of symmetry. It looks the same from every direction, but it is also wildly unstable. The slightest disturbance will cause it to fall and roll in one specific direction. When it lands, the perfect symmetry is broken. The ball now has a definite orientation, a chosen path, and the universe it represents has taken on specific properties. In the fiery infancy of our cosmos, the fundamental forces gravity, electromagnetism, and the nuclear forces were likely fused into a single, supremely symmetric superforce. The hidden dimensions of string theory were uncurled and dynamic. As the universe expanded and cooled in those first fractions of a second, it underwent a series of these cosmic phase transitions. Think of water vapor cooling into liquid water and then freezing into solid ice. Each transition represents a loss of symmetry and a gain in structure. The vapor is uniform and free, the liquid has a surface, the ice crystal has a rigid, specific lattice. In the same way as the universe cooled, the unified superforce broke apart into the distinct forces we know today. With each break, with each force peeling away, the underlying fields that determine our constants snapped into new configurations. The values for the speed of light, the strength of gravity, and the fine structure constant were not chosen randomly. They were frozen into place like the specific crystalline pattern of an ice lattice, by the way the universe's symmetry broke as it cooled. This transforms the constants from arbitrary, eternal numbers into cosmic fossils. They are the frozen echoes of the universe's first and most dramatic transformations. The near constancy we observe today is simply because the universe has been in this same low-energy, broken symmetry state for almost 14 billion years. The dials were set in that furious initial moment and have barely budged since. Our entire physical reality, then, is the legacy of a sequence of ancient cosmic choices, locked in when the universe was less than a second old. A universe with a drifting fine structure constant is not just a mathematical curiosity. It is a silent, invisible saboteur of reality as we know it. The most immediate and catastrophic effects would unfold within the hearts of stars. Those vast, brilliant furnaces are not simply burning fuel. They are performing a precise, multi-step alchemy. Deep inside a star like our Sun, the process begins with hydrogen fusing into helium. But for heavier elements like carbon, the essential backbone of life, a more delicate dance is required. Two helium nuclei fuse to form an unstable form of beryllium, and before that fleeting beryllium can fall apart, it must capture a third helium nucleus. This three-way collision is a cosmic race against time, and its success hinges on a precise, resonant energy level within the resulting carbon nucleus. This resonance is exquisitely tuned by the strength of the forces inside the atom, which is governed by the fine structure constant. If alpha were just a few percent different, that perfect resonance would vanish. The triple helium process would become astronomically improbable. Stars would still shine, but they would be unable to manufacture carbon. Without carbon, the next step, the fusion that creates oxygen, would also fail. The periodic table of elements would be truncated, stopping at helium and beryllium. A cosmos without carbon is a cosmos without chemistry as we understand it, without planets like Earth, and without the possibility of life built on complex molecules. The stellar forges would fall silent, producing only the lightest ashes, but the chaos would not stop at the stars. It would rewrite the rules of chemistry on every world. The fine structure constant dictates the size and shape of an atom's electron orbitals, the fuzzy clouds where electrons reside. These orbitals determine how atoms link together, the strength of their bonds, and the very architecture of molecules. A slightly stronger alpha would pull electrons closer to the nucleus, shrinking all atoms. This seemingly minor change would have seismic effects. The angles at which atoms bond would shift. The energy required to break or form a bond would be different. Water, the universal solvent essential for all known biology, might not be a stable liquid at Earth-like temperatures. Its unique properties, like surface tension and its ability to dissolve salts, could vanish. More complex molecules, like the long chains of DNA that carry genetic information, rely on a delicate balance of forces to maintain their twisted, stable structure. Alter the underlying constants, and that balance is destroyed. The double helix might not form, or it could become so fragile it falls apart spontaneously. In such a universe, the elegant rules of organic chemistry, the entire language of life, would be rendered gibberish. The nightmare scenario is not one of explosions or cosmic violence, but of a silent, profound sterility. It is a universe where the building blocks of complexity are never forged, and where the rules of assembly are lost. The drifting of a single, pure number reveals a terrifying truth, that the stage for life is not a sturdy platform but a tightrope, and we exist in the grace of its perfect, and possibly temporary, tension. A stronger gravitational pull in the youthful universe would not be a minor adjustment. It would be a cosmic accelerant, fundamentally altering the life cycle of everything within it. Stars are born from the collapse of vast clouds of gas, a process driven by gravity's relentless inward tug. If that tug was fiercer in the past, star formation would have been a more violent, rapid affair. Gas clouds would have crumpled into stellar furnaces with far greater speed and efficiency, but this gift of faster birth comes with a terrible price. Once ignited, a star's life is a constant battle between the outward pressure of nuclear fusion in its core and the inward crush of its own gravity. With a stronger gravitational constant, the crush wins by a larger margin. The core is squeezed tighter, raising its temperature and pressure to extremes. This forces the star to burn its nuclear fuel at a reckless, furious rate. A star like our Sun, which has a lifespan of roughly 10 billion years under our current constants, might blaze through its entire supply of hydrogen in just a few billion years or even less. The most massive stars, destined to explode as supernova, would live even shorter, more frantic lives. This accelerated stellar life cycle means the first generations of stars would have flared into existence, burned white-hot, and died in cataclysmic explosions much earlier in cosmic history than our models predict. The heavy elements forged in their cores, the carbon, oxygen, iron, and silicon necessary for rocky planets and life, would have been scattered into the galaxy far sooner. This earlier enrichment of the cosmos with stardust would, in turn, have allowed the second and third generations of stars and the planets around them to form much earlier as well. The entire chronology of cosmic structure, the carefully mapped sequence from the first stars to the first galaxies, would be compressed and shifted back in time. Our telescopes, which peer deep into the past, might then see a universe that matured surprisingly fast, filled with ancient galaxies that look older and more developed than our standard timeline can comfortably explain. This is not merely changing a number in an equation. It is pressing fast forward on the entire cinematic history of the cosmos. The universe's calculated age itself, derived from measuring its current expansion rate and rewinding the tape, would also be thrown into doubt. That calculation assumes the strength of gravity has always been the same, providing a consistent braking force on the expansion. If gravity was stronger in the past, it would have slowed the early universe's expansion more aggressively. To arrive at the vast, spread-out universe we see today from that more powerful early break, the cosmos would need to have been expanding for a much longer time. Alternatively, the initial explosive energy of the Big Bang would have had to be unimaginably greater to overcome the extra drag. Either way, our confident estimate of 13.8 billion years becomes a question mark. This single variable challenges the well-established sequence we have built from the afterglow of the Big Bang to the present web of galaxies. The cosmic microwave background, that pristine baby picture of the universe, would have formed under different physical rules, its subtle patterns encoding a story we might be misreading. The smooth growth of structure from those tiny ripples would follow a different rhythm. We are left with a profound puzzle. If the force that sculpts the cosmos is itself a shape-shifter, how can we ever be sure of our place in its timeline? Einstein's elegant universe would not merely bend under shifting constants, it would shatter. The theory of general relativity is a breathtakingly precise machine, and its gears are locked together by the assumption that big G, the gravitational constant, is absolutely fixed. If G were found to vary, the entire mechanism would seize. The reason lies in a sacred principle called the conservation of energy and momentum. In simple terms, this principle states that energy cannot be created or destroyed, only transformed, and that the total momentum in a closed system remains constant. It is the bedrock of all physics. In Einstein's equations, a constant G is essential for upholding this conservation law across the curved landscape of spacetime. If G began to change, say, weakening over billions of years, then energy would effectively be leaking out of the gravitational field itself, or perhaps being injected into it from nowhere. The universe's total energy ledger would no longer balance. This is not a small accounting error. It is a fundamental violation of reality's most trusted bookkeeping rule. To accommodate a varying G, physicists would be forced to tear out the very foundations of general relativity and rebuild gravity from the ground up, likely by introducing a new dynamic field that interacts with matter and whose evolution dictates the strength of the pull we feel. The beautiful geometric picture of gravity as the curvature of spacetime would become far more complex, perhaps even secondary to this unseen field's behavior. The equations that predict black holes, gravitational waves, and the expansion of the cosmos would all be rendered provisional, awaiting a complete theoretical overhaul. The demolition would be even more absolute if the speed of light, c, were variable. Special relativity, the precursor to Einstein's grand theory, is built on a principle called Lorentz invariance. This is the formal statement that the laws of physics are the same for all observers moving at constant speed, and that the speed of light in a vacuum is the same universal constant for every one of them, regardless of how fast they are moving. This single, unwavering speed is the linchpin. It is what mixes space and time into spacetime and enforces causality, the law that cause must always precede effect. If the speed of light were different in different directions or at different times in cosmic history, Lorentz invariance would be broken. The consequences are almost too bizarre to fathom. The experience of time itself would become unhinged. Time dilation, the effect where a moving clock ticks slower, depends critically on a fixed c. If that anchor were pulled, the slowing of time could become arbitrary, different for different types of particles or for light traveling in different directions. The famous equivalence of mass and energy, E equals mc squared, would lose its universal meaning. If c were larger in the past, the energy contained within a speck of matter would have been incomprehensibly greater, rewriting the entire thermal history of the early universe in ways that likely contradict everything we observe. Most fundamentally, the very order of events could become ambiguous. Causality relies on a fixed speed limit to prevent influences from traveling backward in time. A variable speed limit could, in some theoretical frameworks, open pathways for information to loop back on itself, creating paradoxes where an effect could potentially precede its cause. To salvage physics from such chaos, we would need a new metaphysics, a framework where the concepts of before and after, of here and there, are no longer grounded in a constant cosmic glue. The search for a theory of everything would have to begin by answering a more basic question: what, in a universe of shifting rules, even constitutes a law? But the strangest consequences might unfold in the quantum realm, where reality behaves in ways that defy common sense. This microscopic world is governed by its own set of fundamental constants. Planck's constant, denoted by the letter h bar, sets the scale of the quantum itself. It is the fundamental unit of action, the size of the smallest possible step in the dance of particles and waves. The charge of the electron, E, is the fundamental unit of electricity, the indivisible packet of negative charge that defines atomic structure. These numbers are the bedrock of quantum mechanics, the rules of the game for everything smaller than an atom. If these constants were to drift, the game itself would transform into something unrecognizable. Consider the Heisenberg uncertainty principle, a cornerstone of quantum theory. It states that certain pairs of properties, like a particle's position and its momentum, cannot be known with perfect precision at the same time. The more you pin down one, the fuzzier the other becomes. This is not a limitation of our instruments. It is a fundamental feature of reality. The very equation that quantifies this trade-off contains Planck's constant. If h bar were to change, the size of this fundamental fuzziness would change with it. A larger Planck's constant would mean a universe of greater inherent uncertainty, where particles would be even more ghostly and delocalized. The boundaries between objects could become profoundly blurred. A smaller h bar could, in theory, make the quantum world appear more definite, more classical, but at the potential cost of destabilizing the delicate balance that allows atoms to exist. For the stability of matter itself hinges on quantum uncertainty. Electrons in an atom do not orbit the nucleus like planets around a sun. They exist in fuzzy probability clouds or orbitals. The fact that they are not in a precise location is what prevents them from spiraling catastrophically into the nucleus, as classical physics would predict. This quantum jitter, governed by the size of h bar and the strength of the electromagnetic force set by the electron charge E, is what gives atoms their size and solidity. Tweak these constants and you tweak the size of every atom in the universe. More dramatically, the behavior of quantum fields would be thrown into chaos. Our best description of particles is not as tiny balls, but as excited states of underlying, omnipresent quantum fields. The electron is a ripple in the electron field. A photon is a vibration in the electromagnetic field. The properties of these fields, their masses, and the ways they interact are determined by the values of the fundamental constants. A shift in the electron charge, E, would alter the strength with which the electron field couples to the electromagnetic field. This could change the likelihood of particles emitting or absorbing light, rewrite the rules of chemical bonding, and potentially make certain particles unstable that are currently stable. In a region of the cosmos where these constants were significantly different, quantum theory as we know it might not just be modified, it could completely break down. The probabilistic nature of quantum events might give way to even more bizarre, unpredictable behavior. The orderly quantization of energy levels in atoms could dissolve into chaos. The vacuum of space, which we now understand, is not empty but seething with virtual particle pairs popping in and out of existence, could become a far more turbulent and energetic sea, potentially destabilizing the very fabric of spacetime in that region. It paints a picture of a deeply fractured cosmos, where the laws of physics are not merely different from place to place, but where the very logic of reality, the distinction between something and nothing, the predictability of cause and effect at the smallest scales, could be a local phenomenon. The quantum weirdness we grapple with today might be just the calm, stable version of a much wilder, more untamed set of possibilities waiting in the distant dark. This silent rewriting of the laws would trigger a quiet, practical crisis at the very heart of science. If the constants drift, then the foundation of all measurement crumbles. Our most basic units of reality are not arbitrary. The meter, the second, and the kilogram are no longer defined by physical artifacts in a vault. They are defined by the constants of nature themselves. The meter is now defined by how far light travels in a vacuum in 1/299,792,458 of a second, which is, by definition, the distance light travels in 1 second. The second is defined by the vibration of a cesium atom, a frequency set by the fine structure constant. Even the kilogram is now defined using Planck's constant from the quantum world. These definitions were a triumph of metrology, freeing us from imperfect metal bars and cylinders and anchoring our units to the immutable fabric of the cosmos. But if that fabric is shifting, the anchor is dragging. Imagine the meter stick in your mind slowly, imperceptibly stretching or shrinking over centuries because the speed of light itself is changing. A second today would not be the same duration as a second a billion years ago if the quantum vibrations of atoms were different. This is not a theoretical curiosity. It is a direct assault on our ability to compare, to communicate, and to build. Every precision instrument, from the atomic clocks that enable GPS to the interferometers that detect gravitational waves, is calibrated against these constants. Our entire technological civilization relies on the assumption that a measurement made in a lab in Tokyo today means exactly the same thing as a measurement made in a lab in Paris next year, or on a spacecraft orbiting Jupiter a decade from now. If the constants vary, that assumption fails. The data from a deep space probe, painstakingly collected over years, would become impossible to interpret accurately because the rules of physics it used to operate and measure were subtly different when it left Earth. The meticulous historical records of astronomy, the light from ancient supernova used to measure cosmic expansion, would be encoded in a language whose alphabet was slowly changing. We would lose the ability to have a coherent conversation with the past or the future, or even with distant parts of the present universe. Science depends on reproducibility, on the idea that an experiment performed under the same conditions will yield the same result anywhere, anytime. A universe of drifting constants makes a mockery of that principle. The conditions are never the same because the very rules that define the same are in motion. This philosophical crisis reaches the core of what science is, a search for universal truths. If the truths themselves are local and temporary, written in fading ink, then the grand project of understanding reality becomes a race against a clock we cannot see, trying to decipher a message that is rewriting itself as we read. The universe, however, is a master of illusion. Before we rewrite the textbooks, we must confront a sobering possibility. What if the whispers of changing constants are not messages from a shifting reality, but simply echoes of our own incomplete understanding? The scientific community is rightly skeptical, and powerful counter-arguments urge caution. The primary challenge is distinguishing a true signal from systematic error. Measuring the subtle shift in spectral lines from quasars 10 billion light-years away is an exercise in extreme precision, pushing our finest telescopes and detectors to their absolute limits. Unknown instrumental effects, subtle miscalibrations in the optics, or even the way starlight is scattered within our own atmosphere could imprint a false pattern on the data, mimicking the signature of a drifting constant. It is like trying to hear a pin drop in a thunderstorm while wearing headphones that might have a faint, inherent hum. Scientists work tirelessly to model and subtract these potential errors, but an undiscovered systematic flaw remains the most conservative and often most likely explanation for any anomalous result. Beyond our instruments, the cosmos itself may be tricking us. Our interpretation of the quasar barcodes relies on models of atomic physics that were developed in pristine laboratories on Earth. But the vast clouds of gas that absorbed that ancient light were not in a lab. They existed in environments we can barely comprehend, subjected to strange magnetic fields, turbulent motions, or densities far different from anything we can replicate. Could unknown interstellar physics, conditions in those ancient clouds we have not yet imagined, subtly alter the absorption lines in a way that masquerades as a change in alpha? It is a real possibility. We are applying the rules of a quiet neighborhood to the conditions of a primordial hurricane. Finally, there is the framework itself. To interpret the light from a distant quasar, we must run it through our cosmological model. We must account for the expansion of the universe, the redshift of the light, and the geometry of spacetime along its path. This model, while incredibly successful, is built on assumptions, including the constancy of the very things we are testing. If our model of cosmic expansion is slightly wrong, or if our understanding of how light propagates across such immense distances is incomplete, it could warp our interpretation of the data. We might be misreading a flaw in the map as a feature of the territory. This is the rigorous, self-correcting heart of science at work. Extraordinary claims do not just demand extraordinary evidence, they demand evidence that survives an onslaught of skeptical scrutiny from every conceivable angle. The current state of play is not a stalemate, but a necessary and healthy tension. It is the process by which a fleeting anomaly is either solidified into a discovery or revealed as a mirage. The possibility remains that the constants are steadfast, and we are simply seeing the complex universe through a glass, darkly. The profound unease of fine-tuning leads us to the edge of an even grander possibility. If the dials of reality can be set to different values, who or what did the setting? One compelling answer removes the need for a cosmic tuner entirely by proposing a staggering new landscape, the multiverse. This is not merely a science fiction trope, but a serious theoretical framework emerging from the frontiers of cosmology and string theory. In this view, our universe, with its specific, life-friendly constants, is just one bubble in a frothing, infinite sea of other universes, each with its own unique, randomly selected physical laws. The speed of light, the strength of gravity, the fine structure constant, all could be different in these other realms. Some universes might have gravity so weak that matter never clumps into stars. Others might have a nuclear force so strong that everything is locked into iron from the first moment. In an unimaginable number of these bubbles, the constants would be incompatible with any form of complexity, rendering them sterile and dark. But in a rare few, by sheer statistical chance, the numbers would line up just right to allow atoms, chemistry, and eventually, observers like us to emerge. This reframes the entire fine-tuning puzzle from a miraculous accident into a cosmic selection effect, often called the anthropic principle. We should not be surprised to find ourselves in a universe that permits our existence. We could not exist anywhere else. Our particular set of constants is not a designed miracle, but a winning lottery ticket drawn from an infinite stack of losing ones. This idea finds a potential home in the inflationary multiverse model, where the rapid expansion of space in the early cosmos could spawn countless bubble universes, each undergoing its own symmetry, breaking and freezing its constants into different configurations. String theory adds another dimension to this, suggesting a vast landscape of possible universes, perhaps 10 to the 500 different versions, each corresponding to a different way for the extra dimensions to curl up, each yielding a different set of physical laws. In such a meta-reality, the question why are our constants what they are transforms. It becomes why do we find ourselves in this particular bubble? And the answer is simple, because this is one of the very few bubbles where that question could ever be asked. The search for varying constants then takes on a new meaning. It becomes a search for fingerprints from neighboring bubbles, or evidence that our local patch of reality is just one possible expression of a deeper, vaster, and more varied cosmic tapestry. While the multiverse offers a grand answer, the search for proof remains here and now, in the quiet confines of a laboratory. If the fine structure constant is drifting, we should be able to catch it in the act, not just in ancient starlight, but in real time. This is the promise of the most precise machines ever built by humankind, atomic clocks. These are not ordinary timepieces. They are exquisitely sensitive detectors that measure the very heartbeat of reality, using the natural vibrations of atoms as their pendulum. At their core, atomic clocks work by locking onto a specific transition within an atom, the moment an electron jumps between two precise energy levels. When it does this, it emits or absorbs electromagnetic radiation at a fantastically stable frequency, a pure, unchanging note in the symphony of physics. This frequency is a direct product of the fine structure constant. If alpha were changing, even by the tiniest amount over a year, that atomic note would very slowly shift in pitch. The challenge is that one clock, no matter how perfect, cannot detect this shift on its own. It would simply keep time according to its own, possibly changing, atomic rhythm. The ingenious solution is to build two different types of atomic clocks side by side, each based on a different atom with a different electron transition. Think of it as having two perfectly engineered tuning forks, one made of aluminum and one of beryllium. Each fork vibrates at a frequency determined by the laws of physics, laws that depend on alpha. If the fundamental constant drifts, it will affect the two tuning forks in slightly different ways. Their perfect harmony will begin to waver. One will tick ever so slightly faster relative to the other. By comparing the ticks of these two clocks over months and years, scientists can watch for any divergence, a telltale sign that the underlying rules are in motion. This is not a thought experiment. At the National Institute of Standards and Technology in the United States, physicists operate a clock so precise it would neither gain nor lose a second in over 30 billion years. It compares the vibrations of a single aluminum ion to those of a single beryllium ion, both held nearly motionless by electric fields and lasers in a vacuum colder than outer space. This aluminum-beryllium clock is essentially listening for the universe changing its tune. Every day, it compares its two atomic hearts, searching for the faintest whisper of desynchronization. Other experiments compare clocks based on different principles entirely, like optical clocks using strontium atoms with microwave clocks using cesium. Each comparison is a new test, a new ear tuned to the cosmic static. The beauty of this approach is its directness. It sidesteps the complexities of interpreting ancient light from chaotic interstellar clouds. Instead, it creates a controlled, pristine environment where the only variable left is time itself. It transforms the question from a historical one into a present-tense investigation. We are no longer just archaeologists of the cosmos, digging for clues in fossilized light. We have become sentinels standing watch in real time, waiting to see if the foundation beneath our feet is, at this very moment, beginning to subtly tilt. Gravitational waves offer a completely new kind of sense for this investigation. In 2017, astronomy was forever changed when detectors on Earth felt the faint ripples from a cataclysm 130 million light-years away, the collision of two neutron stars. For the first time, we not only heard the spacetime shudder of such an event through gravitational waves, but also saw its brilliant afterglow across the entire electromagnetic spectrum, from gamma rays to radio waves. This single event, known as GW170817, opened a new testing ground for the constants of nature. The gravitational waves and the flash of light were messengers from the same violent source, but they travel according to different rules. Gravitational waves are ripples in the fabric of spacetime itself, so their speed is thought to be governed by the geometry of the universe and the strength of gravity, big G. Light, however, is an electromagnetic wave, its speed set by the properties of the electromagnetic field. In our standard models, both travel at the same ultimate speed, the speed of light, c. But what if there is a subtle difference? The two messengers raced across the cosmos for 130 million years. If the speed of gravity were even minutely different from the speed of light, one would have arrived before the other. The fact that the gravitational wave signal and the gamma ray burst arrived at Earth within just 2 seconds of each other after such an immense journey tells us that any difference between their speeds is astonishingly small. This near-simultaneous arrival is a powerful constraint, but it is not the end of the story. The very shape of the gravitational wave signal, the way it chirps up in frequency as the neutron stars spiral inward, encodes information about the strength of gravity in that distant system. By comparing the signal to our theoretical predictions, we can test whether the gravitational constant, G, had exactly the same value in that galaxy 130 million years ago as it does here and now. It is a direct test across both vast distance and time. Every new cosmic collision detected adds another data point, another opportunity to see if the universe's most fundamental force is playing by the same rules everywhere we look. This transforms these distant cataclysms from mere spectacles into precision laboratories, using the fabric of reality as both the experiment and the measuring device. The most pristine laboratory for testing these constants lies not on Earth but frozen in the sky itself. To peer into the universe's first few minutes, we look at its oldest surviving light, the cosmic microwave background. This faint, cold glow is the afterglow of the Big Bang, released when the hot, opaque plasma of the infant cosmos cooled enough for atoms to form and light to travel freely. That moment, about 380,000 years after the beginning, captured a snapshot of the entire universe in its youth. The detailed patterns in this microwave light, the tiny variations in temperature from one patch of sky to another, are like a complex fingerprint. That fingerprint was imprinted by the physics of the very first fractions of a second, governed by the values of the fundamental constants at that time. The precise sizes and distributions of these hot and cold spots are exquisitely sensitive to the strength of gravity, the density of matter, and the rate of the universe's expansion, all of which depend on those foundational numbers. If the constants had been even slightly different during those first chaotic moments, the pattern we see in the cosmic microwave background today would be entirely unrecognizable. It is a fossilized whisper from a time when the dials of reality were perhaps still being set. An even earlier fossil comes from the first 3 minutes. This era, called Big Bang nucleosynthesis, was when the universe was a seething nuclear furnace, hot and dense enough to fuse the primordial soup of protons and neutrons into the first atomic nuclei. The process forged the lightest elements, hydrogen, helium, and trace amounts of lithium and deuterium. The final cosmic abundance of these elements, measured in the oldest stars and gas clouds, is not random. It is the direct, calculable outcome of a race between the universe's expansion rate, which was pulling things apart, and the nuclear reaction rates, which were trying to build things up. Both of these rates are dictated by the constants: the strength of the nuclear force, the gravitational constant governing the expansion, and the fine structure constant influencing atomic stability, all played a role. The observed abundances of, for example, helium-4 and deuterium match our theoretical predictions with stunning accuracy, but only if we assume the constants had precisely their current values during that brief, fiery window. This agreement is so tight that it places our most stringent constraints on how much the constants could have varied in the universe's first few minutes. The light elements we see are a cosmic receipt from the dawn of time, and the numbers printed on it tell us the settings of reality's machine were already locked in. Any significant deviation from today's values would have produced a universe with far more helium or far less deuterium than the one we actually observe. These two ancient records, the cosmic microwave background and the primordial elements, act as unbreakable seals on the early universe. They tell us that if the constants are changing, that change must have mostly concluded within the first fraction of a second, leaving the values we know firmly in place by the time the universe was just minutes old. The search for variation, then, becomes a hunt for the faintest of echoes from a time before time itself had settled into its familiar rhythm. This relentless pursuit of a shifting foundation leads us to the greatest quest in all of physics. The search for a drifting constant is far more than a cosmic audit. It is a potential treasure map to the ultimate prize, a single, elegant framework that explains every force and particle in the universe, a so-called theory of everything. For over a century, our understanding of reality has been split into two magnificent but incompatible kingdoms. On the vast cosmic scale, Einstein's general relativity describes gravity as the curvature of spacetime. On the tiny quantum scale, the Standard Model describes the other three forces, electromagnetism and the nuclear forces, as exchanges of particles. These two rulebooks are both spectacularly successful, yet they speak completely different mathematical languages and break down when forced to describe the same event, like the center of a black hole or the first instant of the Big Bang. Unifying them is the holy grail of modern physics. This is where the mystery of the constants becomes a potential guide. Leading candidates for a unified theory, most notably string theory, propose a breathtaking solution to this divide. They suggest our familiar universe of three spatial dimensions and one of time is merely a stage within a far grander reality. The theory posits that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating strings. And for the mathematics of these strings to work, they must vibrate in a space that has more dimensions than we can perceive, often 10 or 11 in total. Where are these extra dimensions? The theory suggests they are compactified, curled up on themselves at scales a billion times smaller than an atom, hidden from every instrument we possess. But here is the profound connection. The size and shape of these hidden, curled-up dimensions are not necessarily fixed for all time. They could evolve slowly and subtly as the universe ages. And the values of the fundamental constants we measure in our four-dimensional world, like the fine structure constant or the strength of gravity, are directly determined by the geometry of these unseen dimensions. Think of it like the tone produced by a violin string. The pitch depends on the string's tension and length, properties you set. In this cosmic analogy, the constants are the notes we hear, the observable laws of physics. The hidden dimensions are the tuning pegs and the fingerboard, the unseen geometry that determines the pitch. If the tuning pegs slowly turn, the note drifts. Therefore, detecting a variation in a constant like alpha would not be an isolated anomaly. It would be the first experimental whisper from these hidden dimensions, a direct signal that the geometry of the cosmos is more complex and dynamic than we ever dreamed. It would be tangible evidence that we are living on a four-dimensional slice of a higher dimensional reality. This transforms the entire investigation. We are no longer just asking if a number has changed. We are asking if we have finally detected the shadow of a deeper architecture, the first clue that could bridge the chasm between gravity and the quantum world. A verified variation would be a beacon, pointing theorists toward the specific version of string theory or another unified framework that correctly describes our evolving cosmos. The drifting dials of reality might be the very compass we need to navigate toward a complete understanding of everything. Our existence in this precise cosmic moment may be the ultimate selection bias. This is the heart of the anthropic principle, a logical lens that becomes far more haunting when applied to a universe of drifting constants. If the dials of reality can turn, then the stable, life-friendly values we measure today are not a universal truth. They are simply the local conditions of our particular era and our particular corner of the cosmos, a fleeting oasis of order in a much wider and wilder landscape of physical possibility. We find ourselves here because this is one of the rare places and times where the numbers lined up to allow atoms, stars, planets, and ultimately, observers to form. It is a cosmic version of the survivor's fallacy, where we mistake our own unlikely survival for evidence that the situation was never dangerous. This line of thinking casts a long, unsettling shadow, often called the Anthropic Shadow. It suggests we might be living in a temporary bubble of stability, a Goldilocks zone in both space and time where the constants are just right for now. The profound implication is that this bubble may not last. If the underlying fields that dictate these constants are truly dynamic, evolving over cosmic eons, then our current stable configuration could be a phase, a plateau on a much longer journey. The forces that gently hold atoms together today might slowly tighten their grip or relax their hold over billions of years. What happens when our local oasis begins to drift? A future shift in the fine structure constant, even one too slow for our atomic clocks to yet detect, could gradually rewrite chemistry over astronomical timescales. The bonds in complex molecules, the very reactions that power life, could become less efficient, then unreliable, and finally impossible. Stars, whose brilliant stability is exquisitely tuned to the current strengths of gravity and nuclear forces, could see their delicate balances disrupted. Their lifespans could shorten dramatically, or their internal furnaces could falter, leaving future cosmic epochs dark and sterile. This introduces a chilling possibility, a potential expiration date not on life itself, but on the very physics that makes life conceivable. The universe may have windows of habitability that open and close as its fundamental settings evolve. We may be living in one such window, blissfully unaware that the laws we consider eternal are, on a grand enough scale, merely seasonal. This is not a prophecy of doom, but a profound shift in perspective. It asks us to see our cosmic home not as a permanent stage with fixed rules, but as a dynamic process, a chapter in a much longer story whose later pages may be written in a completely different language. It transforms our search for understanding from mapping a static landscape to reading the currents of a flowing river, reminding us that we are not just inhabitants of the universe, but passengers in time, witnessing a particular and perhaps transient arrangement of reality's deepest principles. So where does this leave us in our search for a shifting reality? The current scientific consensus is one of profound caution, but not closure. After decades of meticulous observation, from ancient quasar light to the quiet hum of atomic clocks, no conclusive, universally accepted evidence has emerged that any fundamental constant has changed. This is a powerful statement in itself. It tells us that if the dials of reality are turning, they are doing so with an almost unimaginable subtlety, a slowness that defies our most sensitive attempts to catch them in the act. The search has not been a failure, far from it. It has succeeded spectacularly in tightening the constraints, placing limits on how much any constant could possibly drift. We now know, for instance, that the fine structure constant could not have changed by more than a few parts in a million over the last several billion years. The speed of light and the speed of gravity are equal to within 1 part in a quadrillion. These are not loose bounds, they are statements of incredible precision, carving away vast realms of possibility and forcing any theory of varying constants into an exceedingly narrow corner. The universe, it seems, is either remarkably constant or an exceptionally slow and careful shape-shifter. This relentless narrowing of possibilities is itself a form of discovery, and it is driving innovation at the very frontiers of science. The need to test these exquisite limits has spawned a technological revolution in measurement. The atomic clocks that listen for a drifting alpha are marvels of quantum engineering, creating conditions of such stillness and control that they are, in effect, new scientific instruments for probing the fabric of time. The detectors that captured gravitational waves opened an entirely new window on the cosmos, providing a fresh and independent way to test the uniformity of gravity across vast distances. Each new constraint forces theorists to refine their models, to make more precise predictions, and to imagine ever more clever ways to test them. The hunt for varying constants has become a powerful engine for progress, pushing both our tools and our ideas to their absolute limits. And so, the door remains tantalizingly open, just a crack. The possibility has not been ruled out for very subtle, very slow, or perhaps directionally dependent variations. Changes so minute they hide just below our current threshold of perception, or patterns so grand we have not yet mapped them across the entire sky. The Australian dipole result, while controversial, exemplifies this lingering mystery. It hints that we may need to look not just back in time, but in specific directions, searching for a cosmic grain in the wood of reality. The ultimate answers may require waiting for the next generation of telescopes, clocks with even greater precision, or the detection of a gravitational wave event from the very edge of the observable universe. We are left in a state of exquisite tension, standing on a foundation that feels solid beneath our feet, while listening intently for the faintest tremor that might suggest it is, after all, slowly moving. This is not a disappointing uncertainty, but the most exciting kind. It means the deepest nature of our universe is still an open question, and the next great discovery could be the one that changes everything we think we know. The journey through these cosmic questions reveals a humbling truth. Our trust in eternal numbers was never a final answer, only a starting point for a deeper investigation. The constancy of nature's constants stands not as a sacred, untouchable truth, but as a powerful, testable hypothesis. This is the true strength of the scientific endeavor, not in defending old ideas, but in having the courage to question the very bedrock upon which they are built. Each meticulous experiment, from analyzing ancient starlight to comparing the ticks of atomic clocks, is a testament to this self-correcting process. Physics does not evolve by clinging to comfort, but by rigorously probing its own foundations, willing to rebuild everything from the ground up if the evidence demands it. This relentless questioning is what transforms a static map of the universe into a living story, one we are still learning to read. Our tools for reading that story are about to become unimaginably sharper. The next generation of space telescopes, like the European Extremely Large Telescope, will collect light from the first stars with unprecedented clarity, giving us a cleaner spectral fingerprint from the dawn of time. In laboratories across the world, quantum sensors and optical clocks are approaching such staggering precision that they could detect a change in the fine structure constant over a single human lifetime. These are not incremental improvements, they are leaps into a new realm of perception. Within the next decade, these instruments may finally provide a definitive answer, closing the book on this mystery or opening a new and even more astonishing chapter. Whatever they find, the pursuit itself reaffirms a beautiful principle. Our universe is a place that invites questioning, and our understanding of it is a journey without a final destination. So keep looking up and keep wondering. The most fundamental rules of reality are waiting for their next test.